we shall talk about spectral properties of line codes. If you may recall, we were interested in looking at the power spectral properties of a line code which may typically look like this, line coded signal which may typically look like this, consisting of positive and negative pulses in general of arbitrary amplitudes with pulse widths equal to, let's say, some value t sub 0 and with a period of t sub 0 which corresponds to the data rate, the symbol rate or the pulse rate that you are using in your digital system, digital transmission system. As we discussed that day, instead of computing the power spectrum of directly this pulse train, it will be more convenient to first look at the power spectrum of a corresponding impulse train whose strengths depend on these amplitudes, or the amplitudes of this pulse train and the impulse strengths in this impulse train are related to each other, because once we have the power spectrum of this kind of an impulse train, we can use that to compute the power spectrum of not only this kind of pulse train but any arbitrary kind of pulse train, in the sense that the pulse shape could be different from the rectangular one we are using here. All we have to do that is to regard this pulse train as having been obtained from passing of this impulse train through a filter whose impulse response is pt, where pt is the shape of this pulse, right? If, for example, you want a rectangular pulse train of width t0, all you need is a filter of impulse response with a width of t sub 0, right? Because passing of this impulse train through a filter of that kind will obviously produce a pulse train of this kind. This hardly needs any explanation. And in that case, the power spectrum of this pulse train yt we obtained in terms of the power spectrum of xt by simply the well-known result. Sy omega here would be S6 omega, which is a power spectral density of the input, multiplied by p omega magnitude square. Alright, this is what we were talking about last time. So we will now be interested in obtaining the power spectrum of this impulse train xt, alright, which occurs periodically. It is not a periodic impulse train, but the consecutive impulses occur every t0 seconds, capital T sub 0 seconds, and they have the impulse strengths in general. The kth impulse has a strength of a sub k occurring at the time instant kt0. Now, how do we go about obtaining the power spectrum of such an impulse train? Any suggestions on that? How do you go about obtaining the power spectrum for an impulse train of this kind?
Spectral density integration.
Any specific definite approaches?
Autocorrelation.
Summation of
Verify the autocorrelation, then take Fourier transform.
Very good. What we have to really do is compute. We have to realize first that these amplitudes are random in nature, right? And therefore we have to obtain the autocorrelation function of this impulse train, at least the time autocorrelation function, and then what is the relationship between power spectral density and autocorrelation function? They are Fourier transform pairs by virtue of the Wiener-Khinchin theorem that you must have heard of. The autocorrelation function and power spectral density function are Fourier transform pairs. That's the result we shall use, and to do that, what we first need to do is compute the autocorrelation function of this impulse train. In order to do that, we shall make another transformation from this impulse train back to rectangular pulses. What we like to do is, and all of you are familiar with this fact, you can regard an impulse as a limiting form of a specific kind of pulse shape that you may choose. For example, we could choose a rectangular pulse shape whose width and height are such that the area under the pulse should be equal to the strength, and in the limit as the width is decreased to 0, the amplitude of that pulse will go to infinity, becoming an impulse with its strength a sub k, right. So we shall do that. We shall therefore approximate to start with this impulse strain once again with a rectangular pulse strain, but with a different purpose now, and in the limit as the width of those pulses is made 0, we shall obtain our impulse strain back. So that is a situation depicted here. Each of these pulses is supposed to approximate the impulse corresponding to it in the impulse strain that sequence that we discussed a few minutes ago. The height h sub k of the kth pulse and the width epsilon k, epsilon will be constant for all pulses, are chosen such that hk epsilon would be equal to a sub k, right. So that in the limit that this epsilon is made 0, area is kept constant by increasing the height, we will again get back our impulse strain, alright. So therefore, to start with, we will not compute the autocorrelation function of the original impulse strain. What we like to do is compute the autocorrelation function of this kind of a pulse strain, and then take the limit as epsilon tends to 0, keeping the area constant. That is the approach we are going to follow. Is the approach clear?
Sir,
yes.
why go from a pulse strain to an impulse strain and then back to a pulse strain? Why can't we just find
It's convenient. We will see that it is very convenient. There are certain kinds of things that we can understand nicely if we follow this approach. We will see that as we go along. Now let us look at the autocorrelation function calculation, which we do by, I will come back to this diagram in a minute, but let us recall the definition of an autocorrelation function that you are all familiar with. So we are, let me just denote this approximation by x hat t, right. Let us remember that xt was the original impulse strain, and x hat t is approximating it by rectangular pulses of vanishingly small amplitudes, vanishingly small durations, epsilon. Alright. So we may recollect the definition of a time autocorrelation function of x hat or x hat tau. How should we define it? We will define it as limit as some t, capital T tends to infinity, in 1 by t into integral from minus t by 2 to plus t by 2 x hat t into x hat t minus tau dt. Okay, that is the autocorrelation function definition. You all recollect this definition? You basically take an observation interval which is sufficiently large, take the original waveform x hat t, take its shifted version with a delay of tau, corresponding to which you want to obtain the correlation between the two waveforms. You are basically obtaining correlation with the lag tau of the waveform with itself, right. So you take an observational interval of length t, compute this integral over these limits, and then take the limit as t tends to infinity. That is the definition of the time autocorrelation function. Now, as when tau is 0, the two waveforms, the undelayed and the delayed versions, will perfectly coincide, and you will get the peak of the autocorrelation function. We will get the maximum value of the autocorrelation function for tau equal to 0, which is a well known property of an autocorrelation function. And also you may remember that autocorrelation function is an even function of tau for real signals, right? That is, whether you delay it one way or the other, the value of the autocorrelation function is same for equal values of tau on both sides, right? So whether you delay it or advance it by tau, you will get the same kind of average behavior of this product, this integral. Let us consider to start with values of delay which are small. Let us consider taus which are small, specifically smaller than the pulse duration epsilon that we are using. Let me show it here. We are considering this waveform and its delayed version, and I have depicted here only one of these pulses instead of the whole of it, because it's not really required. So what you can see is that this dotted waveform is shifted from the original waveform, original pulse, by an amount which is equal to tau, which is shown over here, very small amount, which is less than epsilon, the pulse duration, right? And obviously the contribution to the integral, what we are interested in know is what is the value of this product, because that product is what is going to contribute to the value of this integral. This product will be contributed now by a number of such pulses, right, all of which lie in the interval between minus t by 2 to plus t by 2, which you are integrating, and we are looking at the contribution of the kth pulse pair x between of x hat t and x hat t minus tau, which is depicted like this.
So have you assumed that the gap between two pulses is greater than epsilon?
That's right, because epsilon we anyway assuming to be vanishingly small eventually, right? That is understood. Okay, so what will be the value of the autocorrelation function for this value of tau? Well, it depends on this overlapping area, as you know, and that overlapping area will depend on will actually be proportional to epsilon minus tau. More specifically, it will be hk into epsilon minus tau, right? And every pulse in the region which you have chosen, let's say between minus t by 2 to plus t by 2, will contribute a similar value, but the only difference will be the amplitude hk is different from pulse to pulse. So we can say therefore that for tau less than epsilon, the value of the integral, I will just call it I, value of the integral, will be equal to hk square, because you are multiplying hk with hk in the kth pulse pair situation, into epsilon minus tau, which is the duration of the overlapping interval, right? Or if this is confusing, you can write epsilon minus tau into hk square, so as not to confuse this with the argument of hk or anything like that. This is a product. And this is the contribution to the integral from only the kth pulse pair. Really speaking, I must modify this to be this equal to sigma hk square into epsilon minus tau for all those values of k, all those values of the index k which keep the corresponding to the pulses in the interval between minus t by 2 to plus t by 2, right? So we can therefore write r x hat tau equal to limit as t tends to infinity of 1 by t. I can replace this integral now with this summation, right? Is it fine? Further, I note that hk square, hk is ak upon epsilon, because hk was selected to be such that hk epsilon is equal to a sub k, right? So let us substitute for that, and we'll get ak square into epsilon minus tau upon epsilon square. All right. Any doubts? Please speak out if you have any problem. We'll go proceed further then. Or further, we can write r except tau. I'll define a quantity r sub 0 in a minute upon epsilon t0 into 1 minus tau by epsilon, where let me just quickly get back. That's difficult to see. Let's see like this. This epsilon square I'm taking outside, so that gives you this expression 1 minus tau by epsilon. Actually, you're taking epsilon outside because this one epsilon will cancel, and r0 is defined by limit t tends to infinity t0 upon t. Just convince yourself that this is okay. All right.
So T0 is anything arbitrarily chosen?
No, T0 is the, I have just for some convenience I have introduced this T0. It was not required to be introduced, right? All I really needed to define was limit 1 by t ak square, right? But I have deliberately done it because it is convenient to do so as we will proceed further, right? T0 is the period of
Between two pulses.
is the repetition period of the pulse train. It's not exactly a repetition period, it's the time interval at which the impulses are occurring, or pulses are occurring. Corresponds to a data rate. It's the interval corresponding to a data rate. Fine? So I hope this expression is fine. We can proceed further then. In order to proceed further, the first thing we like to notice is this expression has been obtained under the assumption that tau is positive and less than epsilon. And we already discussed it's an even function of tau. Autocorrelation function is an even function of tau. So the same expression should be valid, or similar expression should be valid for negative tau, except that this will become plus, or better, it is more convenient to write like this: 1 minus mod epsilon by mod tau by epsilon, right? Because whether the shift is on one side or on the other side, you expect the same value of the autocorrelation, right? For the same value of tau, provided mod tau is less than epsilon. What will happen now as tau is increased?
Degrees.
It is
It becomes 0.
If it is less than
Zero.
It's obvious.
T0.
Good, very good.
But before
It
the
will become 0 at what point? At tau equal to epsilon. So you have a triangular shape up to tau equal to epsilon,
0.
and 0 beyond, not entirely beyond, but for some time.
Then overlap with the next one will start.
That's right.
Up to T naught.
So we'll say that this is not really complete expression. This is for magnitude of tau greater than epsilon,
Less than T naught.
but less than
T naught.
T naught, and so on. We'll try to appreciate it more and more as we go along. So is this fine? So as we just noticed, as tau tends to epsilon, Rx at tau tends to 0 because of 0 overlap between the kth pulse of x hat t and the kth pulse of x hat t minus tau. But as tau is increased further,
So excuse me, sir,
yes please,
in the previous expression, it will be 0 for tau is greater than epsilon, but for tau less than t0 minus epsilon.
that's right,
Because the right half of it will start,
That's right.
not the left.
you're right, you're absolutely right. It should be t0 minus epsilon, because as soon as tau becomes t0 minus epsilon, an overlap between two one period displayed version of each other, pulses of each other will start to take place. Very good. Now as tau is increased further, this is what just has been pointed out. The kth pulse of the delayed pulse x hat t minus tau will start overlapping with k plus 1th pulse of x hat t, right? Particularly as tau approaches t0, more specifically at the point when tau becomes equal to t0 minus epsilon, as just been pointed out, right? So what will happen then? We'll get another triangle, right, around tau equal to t0, with the difference that the amplitude of this triangle would be slightly different, because now it will involve product of ak and ak plus 1, right? So I think all of you now appreciate this fact that the R1 that will come into the picture will be limit as t tends to infinity of t0 by t summation over k a sub k into a sub k plus 1, right? Again we are assuming that only those terms will matter for which lie in the interval between minus t by 2 to plus t by 2 that we are considering. Similar things will happen for tau equal to 2 0, tau equal to 3 0, and so on, right? As you
Other expression will also change because in
the corresponding expression for R1, R2, etc. will also change.
so you multiply 1 minus 1.
That will stay as such, because you'll basically you'll get a triangular shape over 2 epsilon period around each t0, around n t0, right? Because as you move around, the overlap first increases. As you approach the next period, the overlap first increases gradually, becomes maximum, and then starts to decrease.
So it won't be that. It will be tau minus kt0 only. Like you put that.
Oh, I'm only talking about the shape, right? Obviously, each of these triangles is centered around nt0 or whatever, tau equal to nt0. You are quite right. Let me show that pictorially. The thing that all of you are actually mentioning is precisely what I also mean. That is, at the center for tau around tau equal to 0, you have a triangle like this of duration 2 epsilon, going from minus epsilon to plus epsilon, an amplitude which is r0 by t0 epsilon. Around t0 you have an amplitude which is r1 by epsilon t0, and so on. Okay. This r0 by t0 epsilon, if you may notice, comes from this over here. Don't worry about it, it's okay. This over here, this amplitude here of the triangle. So this is the autocorrelation function of that approximating pulse train, right? And obviously what we like to do is get back to the autocorrelation function of the original impulse train. Maybe before I do that, we must note that the generalization of this expression would be, this will become R sub n, and everything else is same. This will be A sub k into AK plus n, right? That is the value that will govern the amplitude of the triangle located at tau equal to nt0, right? So R sub n will be governed by the summation A sub k into A sub k plus n. Now, to get back to the original situation, what we like to do is make epsilon vanishingly small, make epsilon smaller and smaller, keeping hk into ak constant, or keeping the area under this triangle constant, right? So, what is the area of this triangle?
R naught but dot naught.
It is twice of this,
R0
sorry, half of this into this, right? So R naught by T naught, right? That is the area. So as we make epsilon smaller and smaller, this amplitude obviously becomes infinity. Once again you get back an impulse located at each of these points.
So shouldn't
The
we
impulse strengths are R0 by T0, right?
shouldn't we decrease epsilon, keeping the condition epsilon into AK equal to HK constant?
No, we are now talking about what will happen to this limit, what will be the limiting form of this this triangular pulse train.
That is true, but to get the corresponding autocorrelation function for the impulses from where we had started by making
No.
reducing the
We have obtained for that pulse train this autocorrelation function, right? As epsilon tends to 0 and that area is kept constant, we get that impulse train. We like to see now what happens to this autocorrelation function, which has an amplitude which also tends to infinity, right? So we get a different kind of impulse train whose amplitudes are these. Okay. So as we get the limiting form of this as the autocorrelation function of the limiting form of the original impulse train whose autocorrelation function we really desired. So as you can see, this will be obviously symmetrical. If this is R1 by T0, this will also be R1 by T0. This should be R2 by T0, not epsilon T0. Similarly, this will be R2 by T0, and so on. So mathematically, we let epsilon tends to 0. This will make the width of each of these triangles tend to 0. Also the height will tend to infinity because the amplitude is R sub n by epsilon T0. There is an epsilon in the denominator of the amplitude, which will make the height of the impulses of the triangles go into infinity. But the area will remain finite, which is equal to R sub n by T0 for each of these. And therefore, in the limit as shown over here, we will get R sub x tau equal to 1 by T0 sigma Rn delta tau minus nt0, n equal to minus infinity to plus infinity, where we keep in mind that Rn is limit t tends to infinity T0 upon T A sub k plus n over k. Right? So this is our result for the autocorrelation function. This is what we like to study in detail in connection with various kinds of line codes which may be of interest to us, which will give us a better insight about what kind of spectral properties do various line codes possess, and therefore what conclusions can we draw regarding their behavior. Before doing that, is it okay? Do I take it away? Before doing that, we should go from the autocorrelation function to the spectral domain, and that we do simply by taking the Fourier transform of this function. I think I can do that here itself so that you can appreciate. Sx omega will be equal to very easy, isn't it? The Fourier transform of an impulse function located at nt0 with a strength r sub n will be given by e to the power minus j n omega t0, n going from minus infinity to plus infinity. Now we can also use the fact that r sub minus n is the same as r sub n, right? And obtain an alternative expression which is dependent only on cosine functions 1 by t0. I have taken out the r0 term here from this, plus 2 sigma n equal to 1 to infinity r sub n cosine n omega t0. Alright. You can combine the positive frequencies and the negative frequencies to obtain cosine terms for non-zero values of n, right? So this is an alternative expression for Sx. This is the power spectrum of the impulse train, and if you remember, we started by saying that we can obtain the power spectrum of a pulse train with an arbitrary pulse shape pt by passing this xt through a filter with impulse response pt, and let us say we are now interested in that power spectrum of a pulse train yt, which uses pulse shapes, basic pulse shape p of t, and obviously we discussed that earlier. Sy omega would be p omega square into this expression over here, Sx omega. I will substitute for that upon t0 r0 right. So that's our general result. Any questions? Incidentally, this pulse shape pt could be totally arbitrary. For example, I could have, in fact I probably have something here. I could have a pt like that, right? This is your basic pulse shape in the interval from 0 to t0, and then you'll get a pulse sequence like that. Need not necessarily be rectangular in shape, right? What may seem desirable from what we have been talking about is that pt should be limited to the interval t0, 0 to t0, right? But as we will see later, in reality we do use pulses in data communication which may not necessarily be limited to the basic data rate interval, right, for reasons which will become clear soon enough. But for the moment we shall impose that condition and consider line codes with this property, right. Any questions? I'll stop for a few questions that you may have. Couple of minutes. What we'll do next is take up various line coding schemes which one may use and see what kind of spectral properties they have and derive important or useful information about them. Any questions? Okay, let's first take the class of unipolar signaling schemes which we have argued out earlier not to be a very good thing to do, right. We'll now see that from a number of points of view that is so. We already seen some, we'll look at them again, but we'll start by looking at the spectrum of a class of unipolar pulse trains. And this class of pulse trains is typically known by the name of on-off signaling. Right? Because when you're transmitting one, you're transmitting a finite energy and a finite amplitude level with a pulse which may have some arbitrary duration. It may not necessarily be equal to T0. The pulse duration need not necessarily be equal to T0. It may not occupy the whole of the interval. If it occupies the whole of the interval, we have one kind of condition. If it doesn't, we have another kind of condition. But first, basically we are talking about the fact that one is represented by a positive amplitude, a positive, maybe negative, but usually positive amplitude, and a 0 by 0. This positive amplitude pulse may have a duration equal to T0 or less, right. When it has a duration equal to T0, we get a situation which is similar to N or Z. In fact, this is the most general name of non-return to 0, right. That is, if your pulse duration T0 is taken to be equal to T0, during a 1 we are not returning to the 0 level, and that is what we call a non-return to 0 signaling scheme, right. If however you take T0 which is less than T0, right, because we are transmitting a pulse, this is your T0, let us say, but pulse width is less than that, even during a 1 you are at a 0 level for part of the interval, right. That's called a return to 0 signaling, unipolar signaling scheme, right. So this is a general definition of N or Z. We discussed only a special case of that last time when we discussed polar schemes, right. But this is the general case of non-return to 0, and this is what is called return to 0. We'll consider both of these under the class of on-off signaling first. Now remember, we have taken for our analysis an interval equal to interval from minus T by 2 to plus T by 2, right, and then of course we are making T tend to infinity. Let us first try to understand what happens, what kind of properties we may like to get, we will get for a sequence of unipolar pulses in this interval. First of all, how many pulses you are likely to get in this interval if T is sufficiently large? Number of pulses in this interval that you will see is of the order of T upon T0, right. A new pulse is coming every T0 second at the data rate, right. So approximately we will get these many pulses, and if T is sufficiently large, and if we assume that ones and zeros are equally likely, that's another assumption we'll make. Then we can go and calculate our autocorrelation function or power spectrum. But the important thing to note here is that your power spectrum depends not only on the pulse shape but also on the specific sequence of AKs that are being used to transmit via those pulse shapes. AKs, the strengths of these impulses also have a bearing on the spectrum. Remember the expression? In fact, I forgot to point this out earlier, but this is a very important fact that one should remember. The power spectrum of S sub x or S sub y depends on these RIs or RNs, and RNs in turn depend on that summation AK into AK plus N, right? So the specific data sequence that you are transmitting is going to have an important bearing on the power spectrum that finally results. Not only just the pulse shape, which is just a multiplying factor. This of course has a very important role to play, the shape of P omega, but equally important is the role of these functions, RIs, RNs. Okay? You must remember that. That is why we have to consider what kind of AKs we are talking about. That is why I have got a model for AKs that we shall use in our calculation of the power spectrum. So, and that is one of the assumptions we shall make, that ones and zeros are equally likely.
Why number of pulses approximately equal to T by T naught? Why not
So what is this,
exactly equal to T by T naught?
Well, I have not said here that T is a multiple of T0 and all those things. One can do that, but since it need not be, then I just, yes.
So when we say the ones and zeros are equally likely,
Yes.
that means we tend to set a particular kind of sequence, strength pattern, AK.
No, a data sequence is random, but in general, if you observe the data sequence over a large period of time, you are likely to see as many ones having occurred as number of zeros, right?
Within this, there may be different sequences.
Within this, you can have an infinite set of sequences, right? So it is hardly imposing any restriction. It is only talking about the fact that your source of data is balanced in ones and zeros, right?
Each combination would have a different spectrum. That is what is reflected by RN, is it?
But since we are talking of averaging of AK into AK plus N over K, right, it is going to become sequence independent more or less, provided the averaging interval is sufficiently large under certain conditions. Strictly speaking, what you are saying is true, but under certain assumptions like ergodicity of sequence and things like that, it will become, time averages become equal to ensemble averages, right? So we are assuming that we can assume that the source is ergodic, in which case even if you compute it for a specific sequence, if the averaging interval is sufficiently large, we can assume it to be more or less representative of the power spectrum for any sequence, as long as this assumption is satisfied. So I didn't want to go into those questions, but since you have raised it, we can assume that the source is also ergodic. Okay, we can replace time averages with ensemble averages with time averages. That is the whole motivation for taking up time autocorrelation function, right? Otherwise we'll have to do a slightly different kind of treatment. We can also do an alternative treatment in which we do a statistical averaging rather than time averaging. By and large we'll get similar results. This is more convenient, so I did this.
If ones are equal, ones and zeros are not to occur with equal probability,
We'll get it.
really this would have mattered. The specific combination
No. It does not affect the expression that we have derived. It will affect what we are going to derive, right? What we are going to derive from this, because we are going to compute the value of Rn, and that computation we are going to do under that assumption. Okay? It doesn't affect this computation. It doesn't affect the result that we already derived, but it is now going to affect, for the specific case of on-off signaling, the conclusions that we are going to reach, right? Okay, so if we assume ones and zeros to be equally likely, what we are saying is the value of AK is going to be 1 for approximately half the number of pulses that we are observing in the interval T, right, which was T by T0. So it is 1 for T upon 20 pulses, and it will be equal to 0 for an equal number of pulses. Consider then, is that alright? Any questions on that? Consider then R0, that is given by limit as t tends to infinity T0 upon T summation A sub k square. Right? Now what can we say about this summation? These, in the observation interval T that we are considering, which is large, AK square is equal to 1 for half the time, right, and 0 half the time. Only those pulses which are 1 will contribute to this summation. Those which are 0 will not contribute to this summation. So this will be equal to T0 by T. This is going to be T by 20 into 1 square, right, because each has an amplitude 1. I have forgotten the limit here because this T and this T will cancel, so it will become independent of T as long as T is sufficiently large. So we will get precisely equal to half. Similarly, consider now R sub n. The case of R sub 0 is okay. Then R0 for this kind of situation will become equal to half, and we shall now consider what is R sub n. No, it is not going to be 0. We will see that. This is equal to limit p tends to infinity. Yes, that's right. Oh, I'm sorry. This should be AK into AK plus n. Now, once you got AK into AK plus n, we can have this pair, consider the pair AK, AK plus n. We can have the values 1 into 1, 1 into 0, 0 into 0, or 0 into 1. Right? And again, under the equally likely assumption that we have made, only 1/4 of these terms will really be contributing to the, assuming that if T is sufficiently large, only 1/4 time we will have this situation. We get this answer to be equal to 1 by 4. Right? Just like we had half over here.
T by 2.
1 by 8.
by 4.
1 by 4, sir.
This is 1 into 1 when it is when they are both 1, and that occurs 1/4 the times. So it becomes this is going to be equal to T0 by 4 T0. T by 4 T0. Right? And we get this. So the conclusion is that R0 equal to half, but Rn equal to 1 by 4 for n not equal to 0. Substitute that in your expression for Sx omega. We get 1 by 4 T0 plus 1 by 4 T0. This is the complex exponential form that I have taken. I have deliberately split the R equal to R0 term into 1 by 4 plus 1 by 4 so that I can write this, right? Now let me give you a small exercise. If you don't know this result already, try to prove this result. This is known by the name of Poisson sum formula. It can be obtained from simple background and signal systems that we already have. We have a result e to the power minus jn omega t0 summation over minus infinity to plus infinity can be written as 2 pi by T0. That's right. Delta omega minus 2 pi n by T0. Please try to prove this result. Okay. This is one of a class of formula known by the name of Poisson sum formulae. Right. Very easy to prove by just looking at the Fourier transform properties, and we shall use that here to get Sx omega equal to 1 by 4 T0. I will substitute this by this over here to give you 2 pi by 4 T0 square delta omega minus 2 pi n by T0. Yes, you have a question?
Isn't xx omega equal to 1 by t naught summation of Rn is to minus j n omega t naught? Where do you get that constant term in xx omega?
This term?
Yes, sir.
I just told you. See, for putting this like that, I must have all the ri's equal, but my r0 is half, others are 1 by 4. So I am splitting this one into 1 by 4 plus 1 by 4, taking off one of the 1 by 4's out and writing like that. Alright? Any other doubts? So today we have a lot of maths, but this is more or less the final point of maths that let's see. Just a few more equations before we start discussing the results. Coming now to Sy omega for an arbitrary pulse shape, this will become P omega square upon 4 T0 into 1 plus 2 pi by T0 delta omega minus 2 pi n by T0, n going from minus infinity to infinity, where P omega is the Fourier transform of Pt. Now let us consider the return to zero situation, assuming that your pulse Pt has a duration equal to T0 by 2. We call it half width rectangular pulses. Okay, so your P omega is going to be, let me specify Pt more precisely. We will denote it by pi. This is just a notation. This is a rectangular. This is a notation for a rectangular pulse of width T0 by 2. Right? Generally, we write T upon tau. This. Sometimes we can also write 2T upon T0. This is just a notation for this kind of a rectangular pulse. What is the Fourier transform of such a rectangular pulse? Sinc function. More specifically, we will not really go into that. Assume that all of you can verify this or already know this. That is this function. And we get our final result, which we shall look at in detail now, which is this. All right. We're just at about 11, so I think we'll have to stop here. We'll look at this expression again next time and try to understand the nature of the power spectrum of the RZ signal and NRZ signal with respect to on-off signaling, and then go on to other forms of line coherent signals.
So do
Yes.
you want explanation nuance derivation or just the final result?
That is something we'll discuss separately, if you don't mind.